first lesson of A2. So we are doing benzene today. It's the first chapter of your organic chem. So for benzene, this chapter, right, it requires all your knowledge from your AS chemistry, especially on your organic. So do not throw any notes you have on your AS organic chemistry. So this lesson, we're going to cover a few things. It's going to be the hybridization of benzene, which you need to know. At the same time, you need to know about all the reactions of benzene and the stability of the ring, electrophilic substitution reaction on benzene ring, as well as oxidation reaction for benzene. So at the end of the day, we're going to talk about the optical isomerism for benzene, which involve we will talk about the racemic mixture as well as your enantiomers and the uses of it. So please follow the lesson and fill up your notes, and I'll see you guys soon. Drink more water. Yeah. Bye. Alright guys, let's go. So let's look at Friedel-Crafts alkylation of benzene and methylbenzene. So guys, what is alkylation, right? So what you need to do, right? You just have to turn, okay, an alkyl benzene, right, into something else, okay? So, okay, never mind. Let me draw it out for you. So alkylation means substituting, highlight the word, substituting a hydrogen group with an alkyl group. So from an alkyl group, right, you're trying to make it into either a methylbenzene or ethylbenzene. Okay, so this process, we call it as alkylation. Okay, so again, guys, what you need to do, right, you have to treat it with an acyl chloride. Okay, so reacts under room temperature. Okay, with acyl chloride. Wait, no, this is not. With a halogenol, okay, my bad. Okay. And sorry, guys, this one, can you change it to this? This is ethyl. This is not. My bad, my bad. I want you guys to put it under reflux, not room temperature. Okay, so guys, again, let's say if you want to turn benzene into methyl or ethyl, right, you have to heat it under reflux with a halogenol alkane. So guys, your halogenol alkane, it's any halogenol like chloroalkane or bromoalkane, anything like that. Okay, in the presence of AlCl3 as a catalyst. You need to have AlCl3 as a catalyst, remember that, yeah? Okay, so here's the reaction, guys. I have a benzene. Yeah. Okay, and I add a CH3Cl. Okay, after adding a CH3Cl, right, you have to hit with AlCl3, which is your catalyst. And eventually, right, guys, what's gonna happen to the benzene? Okay, so this benzene will turn into an alkyl benzene. Okay, you have a CH3 here and a HCl. Okay, and now, guys, let's look at the formation of electrophile. So first step, yeah, again, whenever we are talking about substitution on the benzene ring, you see, right, at first it was a hydrogen, yeah. So what you're doing, right, you're trying to get rid of the hydrogen, turn it into a CH3. That we call it as electrophilic substitution. Remember, any substitute. Hey, ha ha ha! You're alone now. Because all your bestie was here just now. You were in Langkawi, right? So just turn on the aircon. You have to bear with it for a while. Will be a bit cooler later. All right, so let's go. Guys, whenever you're substituting anything in the benzene ring, right, the reaction is always electrophilic substitution. Okay, so your first step, right, is always generation or formation of an electrophile. So let's say, right, this is my electrophile I'm forming, right? Okay, so I have CH3Cl. Okay, so this is a chloroalkane, right? Chloromethane. And I have to add it with AlCl3. So guys, what's going to happen is that this point will break heterolytically and Cl will combine with Al and eventually turns into an electrophile, which is a CH3+. And your AlCl4-. Okay, so do you see that this is our electrophile? So first step, yeah, is always to generate our electrophile, yeah. I'm going out. Makan. Okay, now, so once done, guys, let's look at stage one. How the reaction occur. I have a benzene ring. I'm going to throw my electrophile next to it. CH3 plus. Okay, guys, remember, yeah, when you're drawing your curly arrow is always coming from your benzene ring. It's always coming from your benzene ring. Okay, and go into your electrophile. So curly arrow coming from your benzene ring, go into your electrophile. What's going to happen next? Okay, let's say if it substitute on this position, this will turn into a plus, and you have a CH3 here, correct? Then you have a H here, correct? That's it. Insane. All right, guys, next. Let's look at it. Okay, once you have this reaction written down, all right, guys, I want you guys to highlight this carbon again. I want you guys to tell me what is the hybridization state on this carbon. SP, what? 3, well done. SP3 hybridized. Correct. Okay, guys, next. Which means bond angle, please. 109.5. Huyo. Shape, please. Huyo. Hey, not bad. Okay, and guys, next. How many sigma bond on this carbon? 4. Well done. That's 4 sigma bond, yeah, because there's 4 single bond, right? All right, guys, next. If you look at this ring, right, you see that your delocalized ring is broken. So right now, your delocalized ring, your pi ring, right, it's only for 1, 2, 3, 4, 5. Okay, so only 5 carbon will have sp2 hybridized state. Okay, the 6th carbon, it's having sp3 hybridized. Okay, so I want you guys to write it down. So the delocalized pi ring system, this delocalized pi ring system is broken, right? Am I right? And only extended to 5 carbons only, right? Can see. So right now, yeah, your ring is broken, extended to just 5 carbon, yeah. So the 6th carbon is sp3 hybridized already. Can you explain why you get sp3? Because you skipped class last week, ma. Hiya. All right, guys, please tell me why is it sp3? Come. Yeah. Why is it sp3? How you know it's sp3? 4 sigma bond, right? 1, 2, 3, 4. Guys, 4 sigma bond is always sp3. sp2, 3 sigma, and you have a double bond, right? Good job. 1 pi, you have a double bond. sp is when you have a triple bond, right? That's it. Or you have 2 pi bond here. Okay, so can you see that 1, 2, 3, 4, 4 sigma bond is definitely sp3. Okay.
Sir.
Okay, now stage 1 done. Let's draw stage 2. So guys, stage 2, right? Just gonna take this thingy, and what you're gonna do? Oh yeah, what?
Sir.
Yeah.
In your first stage, you know how you drew all those arrows in the equation? Do we also need to draw those arrows?
In exam, no need.
Okay.
In exam, no need. Okay, so what I'm drawing, right, it's to show you where the electron is going. The electron is going from C to Cl, then go into Al. Okay, but in exam, you just have to know how to write this equation, yeah. Okay, but this mechanism, yes, you need to know how to draw. This mechanism is very important. All right, guys, in the second step, the hydrogen, yeah, will break and go back to the ring. Okay, so remember, yeah, the hydrogen break, go back into the ring, and what it turns into, you get your methylbenzene right now. And you have a H plus is produced. Done. Okay, 16. Oh, Kaylin Ho Ho is here. Oh, you Kaylin Alvina Ho. What happened last time? What happened?
I thought I saw your story.
You stole my
No,
story.
okay. I thought you posted face of King.
That's not me, right?
Wait, then
That's Desmond, right? Hey, who's this?
it's a King.
Mr. Kane, yes,
Then I
correct.
thought it was you. Then I was like, wow, switch very raspberry. Then he said, first time buying to try. Then I said, is it good? Bring tomorrow so I can try because usually you always bring your food. I was like, you never use taboo. I realized this Mr. King.
This polar.
Yes. Oh, can I scroll up? Can.
Do you think?
So that means that means hydrogen give 2 electrons from its bond in to the ring, correct? You're right. Hydrogen, 2 electrons go into the ring. As the 2 electrons from the broken system, yes, correct, you're right. You never read my message. I always read your message. What do you mean, Kaylin, Elvina, Ho Ho? When you text me? Okay, Abby, can I see the top page, please? Sama. Sutla. Okay, once done, next. Okay, the hydrogen is removed by the AlCl4 minus, okay, which was formed at the same time, blah, 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 blah. Then aluminium chloride is regenerated. This catalyst is regenerated in the second step. Okay, so guys, now let's say if I have a methyl group. Okay, so guys, let's say if you have a methyl group, right? And I'm trying to add maybe a C2H5Cl here. Okay, so guys, still remember what did I mention about electron donating group? This is an electron donating group, right? EDG, right? Still remember EDG will activate which 2 position? 1, 3, 5 or 2, 4, 6? 2, 4, 6. Guys, remember this you have to memorize. Guys, right now your activating position, you have to memorize it already. It's no longer served in your data booklet, so you have to memorize it already. Remember this. LQ group, it's an electron donating group. When you have an electron donating group, it will open up position 2, position 4, position 6. Understand? Okay, so any substitution is gonna go into 2, 4, 6 position, understand? Because of electron donating property. So let's say, you see, you have this methyl group, this position is gonna get open up, this position open up, this position open up. Okay, so the substitution can occur in either the second position or the 4th position, right? So I can either draw my C2H5 here or draw my C2H5 here. Is that right? Clear? All right, guys, next. Reactant. Okay, I need a benzene or an LQ benzene. Yeah. I have 2 more coming in. Which one is the major product? No, there's no major product in this. It's just a mixture of product. Both are major, you can consider. Okay, there's no major. This is not a major or minor. Okay, so guys, what you need to do, you have to hit with a reflux. Hit under reflux, not hit with reflux. Hit under reflux with AlCl3 and a halogenoalkane, right? So guys, I'm starting off with a benzene. And it's going to turn into an LQ benzene. If you were to further substitute it, you are getting either a 2 or 4 di-LQ benzene, right? Alkane, K-A-N-E. Alright guys, remember if you are substituting anything on the ring, okay, in the benzene, It's always electrophilic substitution. Done. Please check. Okay. My tenants, please write it down. Let's go. All right, kid, once done, page 17, yeah. All right, guys, what do we have? Fredecraft acylation. Okay, so you are adding this carbonyl group in it. Okay, so you have a C double bond O, C double bond O. Okay, hey, I have two more check coming. Can you scroll up to page E? Why so slow? Go, 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 faster. Can I? Okay. Nice. Okay, guys, now, so let's say, right, if you want to introduce a C double bond O in, okay, so before we do it, I want you guys to look at this compound. So, kid, let's say, right, if you just have a C double bond O and a H, okay, so the name given is a phenol, yeah. Okay, so C double bond O and a H, like a ketone group, right? Or aldehyde, we call it as a phenol, like ethanol, propanol, okay, phenol. Okay, that's it, phenol. All right, guys, next. Benzene is treated with acyl chloride. Acyl chloride, general formula is RC double bond OCl, which you will do it later. It's a new organic compound, and AlCl3, and under reflux. Remember, yeah, you have to hit it under a reflux. All right, guys, next, let's continue. All right, kid, I have a benzene ring, ding, and I'm gonna add a acyl chloride. Okay, so CH3COCl, and this acyl chloride is gonna get substituted onto the benzene ring, and you are getting a C double bond O, CH3, and a HCl. That's it. All right, that's the reaction. Sujai is here. All right, guys, once done, next. So the electrophile is often formed by adding aluminum chloride catalyst. Again, guys, your first step whenever you are substituting anything into the benzene ring, your first step is always to create electrophile. Yeah? So first step is to create electrophile. All right, guys, now let me show you how the reaction look like. I have a CH3, C double bond O, and a Cl, right? Okay, I'm gonna add it with a AlCl3. How? What's gonna turn into? Should remember how it break. Delta plus, delta minus, break here, electrons fly here, correct? So it turns into that. You have a CH3, C double bond O with a positive, right? This is your electrophile, am I right? And you have your AlCl4 minus. By the way, your electrophile is formed. Okay, remember, guys, your first step is always to form your electrophile, yeah? Okay, all good. Makan. Wow, healthy way. Not bad, huh? All right, guys, next. Once you have your electrophile, the carbocation electrophile is gonna attack the benzene ring. Kid, I want you guys to draw out the reaction. How does it look like? Go. Draw the reaction. Draw the intermediate now. All right, guys, now done. How does it look like? Again, guys, the curly arrow is coming from your ring. attack your carbon, please. So guys, you go this direction or go this direction, it doesn't matter. As long as it's a curly arrow and it's coming from the ring, attack your carbon, and that's it. So eventually what it turns into, C double bond O, CH3, correct. Then you still have a hydrogen, right? All right, guys, now, you see, just now, okay, so I did a drawing without the reformation of a catalyst. So guys, you see, right, the second step, you can draw with two-way. You can draw with just one arrow from H going in, then you get a H plus, or I can show the catalyst is being reformed. So to show the catalyst is reformed, right, what you need to do, okay, instead of just drawing an arrow going back, right, I'm gonna put my AlCl3 here. This color look a bit sexy. AlCl4 minus. Okay, so the electron is gonna go from your AlCl4 minus to hydrogen first. Then from hydrogen, go back to the ring again. Understand? Okay, so eventually what's gonna happen? I have a ring, and I have this C double bond O, CH3, right? And AlCl3, and you get the HCl, right? Do you see that your catalyst is regenerated? Am I right? Understand? So guys, you can draw it with two different methods, yeah. In exam, it depends on what the exam questions want. Let's say if they want you to show the catalyst is reformed, then you draw it with your AlCl4 minus. Let's say if they never mention, you can just neglect this part, just draw an arrow, then this form as a H plus, also okay. It's not wrong. Okay, so it depends on what the examiner wants. Okay. Today we can move on to phenol. Let me. All right, guys, next. The reaction is just the same as methylbenzene, okay? Except for the fact that, right, what you need to worry about is where the acyl chloride group attached to. So again, guys, this time I'm starting off with a methylbenzene. Dun, dun, dun. Or C2H5, like that. Okay, and I'm gonna add in your CH3COCl. All right, guys, let me test you guys again. Please tell me before I draw out. Guys, what is this? Electron donating group or electron withdrawing group? Electron. C2H5O. LQ group, right? LQ group is always electron donating group, right? Which position is gonna get opened up? Position 2, position 4, position 6. Right now, these three doors are open. Okay, but guys, because this thingy, right, is a fatty. You see, this thingy kind of fat, you know. This it's a fatty. So this fatty, right, cannot go into position 2 because you just imagine, right, you have a C2H5 here already. If you were to sub in, right, you see the fatty will overlap. There's not enough space for it to go into position 2. So it will reorient itself, go into position 4. On one reason, because this thingy is a fatty, very fat. So the fatty cannot go into the second position, go into the fourth position, okay? So, dun, 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 dun. That's it, okay? So guys, now let me write down all the reaction. I have benzene, or I can use an LQ benzene. Okay, condition and reaction. I have to heat under reflux with AlCl3. Plus an acyl chloride, right? Okay, so a benzene is gonna turn into a phenone. Am I right? Let's say if you have an alkyl benzene, so your phenone is gonna suck into the fourth position, right? Yes, there's no further reaction. Okay, so remember, it's gonna suck into the fourth position. So guys, again, you see what you're trying to do? You're getting rid of your hydrogen, sub it with an acyl chloride group, right? So this reaction, it's also electrophilic substitution. Yeah. Done. Alright, guys, let's continue. Okay, kid, right now let's look at the next reaction that we have. It's oxidation of alkyl benzene. That's the last one, the second last one already. So the alkane side chain, okay, of this for example, if I have this, never mind, I should draw it out first before explaining. So I have a side group here, which is a methyl, ethyl, or whatsoever lah, anything. Okay, so I can always oxidize this alkyl benzene, and eventually, right, be it CH3, C2H5, C3H7, things like that. No, I haven't finished the table. We haven't finished the table. You give me a second, later I scroll back. Okay, so this benzene is gonna turn into a carboxylic acid, which we call it as a benzoic acid. And H2O is added. So how many O you need? 1, 2, 3. So 3O. Okay, so this is how we oxidize your alkyl benzene. CH3, C2H5, be it any length you have, you can always oxidize it and turn it into a benzoic acid. Okay, a benzoic acid is formed. Can take place without, cannot take place without, must take place with a side group. If there's no side group, there's no oxidation. Cannot. Okay, now scroll back to the previous page because some kid haven't done the table yet. Go draw. Yeah. Okay, all good. All right, guys, now let's look at the reaction that we need. So guys, I need an alkyl benzene. Remember, must be an alkyl. Oh no, up. Okay, so if it's a normal benzene, it will not work. Must be an alkyl benzene. Okay, because a normal benzene will never work. Oliver, because I have two students named Oliver, right? Can I have your full name? You're Oliver, which? Okay, so what do I need? I need hot alkaline KMNO4. Remember, alkaline KMNO4 not acidified. In AS, right, most of the oxidation is done with acidified KMNO4, right? Yes, correct. Any alkyl benzene will oxidize into a benzoic acid. Okay, so hot KMNO4, and after that, please follow by acidified. Okay, and guys, I have an alkyl benzene. If I oxidize it, it's gonna turn into a benzoic acid. Reaction, oxidation reaction, The C2H5, the carbon will just turn into a CO2. So let's say, right, if you use a C2H5, the second carbon, right, will just turn into a CO2, Kid, I want you guys to look at hydrogenation of benzene. So guys, hydrogenation of benzene is the easiest, basically. Okay, it's a reduction reaction or addition reaction. And what you're adding, right? You're adding hydrogen using a nickel or platinum catalyst? Does it highlight nickel and platinum catalyst? Done. So guys, I have a benzene. And I add hydrogen under nickel or PT catalyst. Okay, and eventually turns into a cyclohexane. Can you see that? This is a cyclohexane. Okay, so guys, again, starting with a benzene, or I can have an LQ benzene, it doesn't matter. Okay, guys, what I need, nickel, platinum, catalyst. Oh, equation of balance, I just realized 3H2 with a hydrogen gas, correct. Okay, and guys, from a benzene, I add H2, it's going to turn into a cyclohexane. Mechanism, addition reaction, or reduction reaction, also it's okay. So this is considered addition or reduction reaction. Are both considered okay.
Sir, what happens to the alkyl group when you add the hydrogen?
Oh, the LQ group just stay. There's no changes to the LQ. What you are changing here, it's the benzene ring.
Okay.
Get it?
Thank you.
Welcome.
That's what I put it.
The LQ group is just LQ cyclohexane. What changes here? It's the benzene ring. It's never the side group. Okay, understand? Boy girl, I'm sending pheno notes over. Okay, I want you guys to look at your pheno note. Please, please, please. Open up your pheno note later, yeah. But no, we're gonna get this done in another. This chapter, I still need about 20 to 25 minutes to 30 minutes. But whoever is printing your pheno notes out, you can go print your pheno note first. All right, guys, now I have a question here. Let's go. I want you guys to start doing the question. So you still have a heat with acyl chloride, heat under reflux with ElCl3 plus acyl chloride. Yeah, which one? This one, right? Oh, under reflux. Sorry, I missed out the reflux, right? Heat under reflux with ElCl3 plus acyl chloride. Yes, sir, you are right. Thank you, Kaylin. All right, guys, next, let's look at this thing. Look at this thing, guys. Again, I have methyl group, right? So what is this? Electron donating group. Which position will open up again? Position 2, position 4, position 6. Remember this, yo. But guys, they already show you a 4-nitro, correct? They want you to form another isomer of 4-nitro, which is the byproduct. Guys, what's the byproduct then? It's just a 2-nitro, am I right? Convert to ink, cancel this part, and just put my nitro on the second position. Done. Okay, it's just a 2 or 4-nitro. Please remember that, yeah. Okay, and guys, you see the temperature they never specify, so should be about 55, because if it's greater than 55, you have 2-nitro group. Okay, next, HNO3 and H2SO4 to form electrophile. Again, nitration of benzene, page 13. Do you see the equation here? Forming electrophile. Remember, first step is always to create electrophile. That is the equation that we are looking for. I'm too lazy. I'm going to copy and paste. So guys, remember, everything is in the note. Okay. So A2 is the same thing. Whatever that is in the syllabus, come out in the exam, is covered in the syllabus, is covered in the notes. Yeah. Wait, why you cannot Why cannot be above 55? Because above 55, you have 2 nitro group. Okay, so I talked about it last week. You can refer to the recording. And next, guys, describe how the structure and bonding on the 6 benzene ring, okay, in the intermediate, of the 6-member ring in intermediate T differs to those in methylbenzene. Okay, I want you guys to refer to hybridization, pi bonding, bond angles. So guys, please tell me, compare a normal benzene ring and intermediate T, what is the difference?
Benzene.
Okay, benzene ring is sp2 hybridized, correct? Then in intermediate T, the hybridized benzene ring is broken, correct? Only spreaded across 5 carbon. So you have this carbon, which is what hybridized? sp3. Bond angle 109.5. Okay, understand? That's it. Okay, so we've done something similar, right? So guys, let's go. I can mention that in intermediate T, so I can mention that the delocalized pi ring system spread across how many carbon? Am I right? So your delocalized pi ring system is broken, right? And spread across, okay, 5 carbon atoms only. Am I right? Correct. All right, guys, next. What about the 6 carbon? This one was a hybridization state. So I can talk about benzene first. All right, guys, please tell me in the hybrid in a benzene, how the structure of in the intermediate DT. Okay, in methylbenzene, okay, I can mention that the delocalized pi ring system made up of carbon with what hybridization state? In the methylbenzene, sp2 hybridized. How many pi bonding? Okay, I already mentioned, right? Pi bonding, then you can mention pi bonding across 6 carbon atom, right? Bond angle 120, right? Thank you so much. So guys, I've done talking about methylbenzene, yeah. Next, let's talk about your intermediate T. So guys, in intermediate T, there's 1 carbon. This carbon, what is it? What hybridized again? sp3 hybridized, tetrahedral 109.5. Okay, am I right? Has sp3 hybridized orbital. Okay, with bond angle 109.5, right? Done. Understand, guys? Can. Sure. It's a 3 marks question, yeah. Know how to write it. Alright, guys, once done, next page. Let's go, boys. Let's look at new syllabus. So, guys, not really new entirely. This thingy is only being introduced after 2022, yeah. Okay, so after 2022. So any past paper before 2022, you're not gonna see this question. But after 2022, every single year, you will definitely have at least 3 to 4 marks from this section, yeah. Okay, so we have optical isomerism and enantiomers. Okay, so guys, should remember what is optical isomer? The mirror image thingy, chiral center. Yes, right. So guys, optical isomer, we have another term given. We also call it as enantiomers. All right, guys, define enantiomers. We call it as molecules, okay, that have same chemical and physical property. Okay, remember a molecule that has the same chemical and physical property but rotate a plane of polarized light into different direction. Crazy. Highlight this entire thingy. Okay, guys, first definition, you need to know how to define, yeah. Oh, good. All right, guys, now let me explain on your racemic mixture. Okay, you don't have to draw anything, just look at it. All right, kid, you see. Okay, let's look at optical isomer first. You should remember how to draw optical isomer. So example, right, guys, you see I have a CH3. Don't need to draw, just look at the board, yeah. Okay, do you see that this is your chiral center? So guys, chiral center, which means if I place a mirror in between, what's gonna happen? It can form a mirror image, right? So I'm gonna draw the mirror image now. Correct. Okay. So guys, this we call it as enantiomer A, enantiomers B. Okay. So guys, what do you mean by that, right? Let's say, okay, so this entire thing is a solution. Just imagine, right, it's found in a beaker. Okay, so this is a solution. A solution containing like enantiomers A, enantiomers B. So let's say if I just take out your enantiomers A, okay, I just take this out, okay, and also I have another, and I separate it enantiomers B. I put it in two separate beaker. Okay, and guys, I'm gonna take a light. So just imagine, right, I'm gonna send a light beam over. So I'm gonna send a light beam from here. Ding, ding, ding. How to draw light beam? Okay, so I'm gonna send a light beam over to enantiomers A. So the moment it enters enantiomers A, right? Okay, so the light, this plane of polarized light will rotate maybe clockwise direction. Okay, for enantiomers A. But if I take the same polarized light and send it into enantiomers B, it's gonna rotate it into anti-clockwise direction. Understand? So guys, you see, this mirror image, right, they are exactly the same, okay? So they are just mirror image of one another. And one property they have is that they will rotate your polarized light into different direction. One will rotate like clockwise, another rotate anti-clockwise. Understand? Please, that we call it as enantiomers. Clear? Okay, so if you want to take a screenshot, you can take a screenshot, or else I'm going to move on. I'll give you guys 30 seconds. If you can understand, then you don't need to. If you need to take a screenshot, take a screenshot. All right, guys, done. Okay, let's go. Can I can move on. Don't ask me to scroll back. Yeah. Okay, guys, let's look at enantiomers, which is your optical isomer. Guys, looking at optical isomer, what are the chemical, what are the property they have that are the same? So optical isomer will always have the same chemical and physical property. Remember, yeah, their chemical and physical property are the same. But what is different? The ability to rotate the plane of polarized light. That is the difference between them. Understand? All right, guys, now, you see. Okay, let's look at this thing. Okay, just imagine, right, I have a solution. In this solution, right, you have 50% of enantiomers A, 50% of enantiomers B. Okay, so I send a light over. If I send over a light, right, what's going to happen? You see, right, just imagine that. So if I send the light over, this thing is going to rotate here. Then when it reaches this, okay, then it's going to rotate to another direction again. So come out, right? You see that there's no change in the polarized light direction. So again, now guys, let's say if you have 50%, 50%, if you have equal amount of both enantiomers in a mixture, there will be no change in the direction. We call it as no net optical activity. Okay, so no net optical activity. Do you see that the light is not being changed? The light is not changing in direction when you have 50%, 50%. Understand? Okay, so this we call it as a racemic mixture. Okay, so a racemic mixture will not cause a change in direction for the plane of polarized light. Okay, but if it's enantiomers, yes, it will. Okay, but if it's racemic, no, it will not. Okay. Done? Alright guys, now let's continue. Yeah. Kid, is it a solution which both enantiomers of compound are present? So if you have both enantiomers compound are present, we call it as a racemic mixture, correct? Okay, so since enantiomers have equal and opposite specific rotation, racemic mixture, highlight this word, racemic mixture show no optical activity. Okay, so optical activity is a property of solutions. Yeah, a racemic mixture contains a mixture of molecule, but it has no net optical activity. All right, guys. Now in exam, this is another popular question whereby they want you to define what is a racemic mixture. Go. How define a racemic mixture again? It's a solution that consists what? Equal amount. Remember, equal amount of optical isomerism, optical isomer with no net optical activity. Understand? Highlight this. No net optical activity. That's it. Clear? Done. So guys, if you shine a beam of polarized monochromatic light through a solution of optically active substance, okay, so the plane will be rotated, yeah. So again, so this part is not in the syllabus. If it rotates clockwise, we call it as positive form. If it rotates anti-clockwise, we call it as negative form. So in A levels, you don't need to know how to name it, yeah. Alright guys, now let's look at some popular question in exam. Okay, so I'm gonna really summarize all the popular and possible exam questions. You just have to copy and paste in your exam. Okay, guys, first, what are the similarities between enantiomers? Both of them will rotate plane of polarized light. They will rotate, but they just rotate in different direction. What else? They have what? Same chemical and physical property, right? Okay, so guys, what's the difference then? They rotate into different direction. Understand? One clockwise, another anti-clockwise. Done. Okay, at the same time, they have different biological activity. Okay, this is something new, different biological activity. Alright, guys, what do you mean by biological activity? So, biological activity, right, as in most of these substances or these enantiomers, right, can be used in skincare, can be used in medicine, can be used as food additive. So basically, when you consume it, right, okay, for example, okay, so if you consume this enantiomers A, it will heal your body. But when you consume this enantiomers B, GG, it will destroy the cell. Okay, so it has different biological activity. Or when you apply this on your face, then it's gonna make your face look younger. But when you apply this on your face, wow, break out, then you get pimples. Okay, so that we call it as different biological activity. So again, enantiomers have different biological activity. Okay, next, what is the benefit of getting a pure optical isomer in medical use? So you have lesser side effect. Okay, then you have higher biological efficiency, okay, and activity of drug and smaller dosage required. These are all the points. Okay, I got you guys all the answers here already. You just have to copy and paste. Okay, guys, what is the disadvantages of forming both enantiomers? I think you put both enantiomers is okay. Or forming a racemic mixture. Okay, so guys, if the reaction forms a racemic mixture, there's a downside. The downside is it requires separation. And guys, how do you separate it, right? It requires a chiral active catalyst. Okay, and finally, how do you produce just one single enantiomers? Is by using a chiral active catalyst. Done. Well. Why would enantiomers, don't they have the same chemical property? But boy, chemical property and biological activity is different. Biological activity is when a living thing is consumed, like when it hits your body, what's gonna happen? Okay, you get me? Chemical property is just a chemical reaction. Yes, biological activity, it's the effect it has on a living thing. You get me? That is biology. Biology is study of living things, right? Okay, so biological activity is the effect it will have on living things, not on chemicals. But wouldn't they have the same chemical reaction? No. Yes, they will not have, they will have same chemical reaction, but again, not all your reactions in your body is chemical reaction. You have biological reaction. For example, when you talk about cell, you see, you have your you have your DNA, right? Double helix, correct? Okay, so you have your ATGC, all these are biological reaction. So, for example, if you take this drug, it's gonna react with your DNA. Another drug is gonna destroy your DNA. That's it. Understand? Now that is biological activity. What is a chiral active catalyst? It's a catalyst that is biased. So if you use a chiral active catalyst, right, you would just get, maybe you just get this and you are not getting this. Okay, that we call it as a chiral active catalyst.
Or you only produce one of the isomers.
Correct, you only produce one of the isomer if you use a chiral active catalyst. Okay? And boy, girl, once done, flip to page 25. Kids, you see, the thing about your new syllabus here after 2022 is that your electron donating group, electron withdrawing group has been removed from your data booklet. Now you have no data booklet, which means you have to memorize. Okay, so example guys, remember all EDG are 2,4 directing, yeah, remember, yeah, EWG is 3,5 directing, yeah. Okay, so EDG is electron donating group, 2,4 directing. Electron withdrawing group is 1,3,5 directing. Okay, please, this is very important. Always come out in exam, and it's not in the data booklet no more, which means you really have to memorize it. All right, guys, now we have some time. Let's do one question. Let's go.
Sir, what is EWG again?
Electron withdrawing group, which
okay.
we will talk about it later on. Right, guys, look at the first question first. Let's try. EDG is mainly LQ group. Yes, you're right. Okay, guys, let's go. First question that we have. What is a chiral active catalyst, guys? Okay, what do you mean by optically active? So optically active means that it will rotate the plane of polarized light. That's it. So I can mention that it's a substance. Okay, that's able to rotate the plane of polarized light. All right, guys, next. Give 2 reasons why it might be desirable to synthesize a single optical isomer rather than, okay, to use as a drug. Why? Why, guys? What is the benefit of using producing just a single enantiomers?
Yes.
Lesser side effect. Well done. Okay, it's in the note, yeah. Well done. Okay, so again, lower dosage is required, right? Well done.
Can say no need to use chiral.
Okay, so no need to use of a chiral active catalyst. So you can mention that, or you can also mention there will be so someone mentioned higher biological efficiency, right? Good job. These are all the possible answer, yeah. Okay, ibuprofen and paracetamol contain aryl benzene functional group. Okay, so name the other functional group which is present. Guys, this is not hard. Get me the answer. What is this? Carboxylic acid. Well done. That's it. Okay, what about paracetamol? Guys, if you have an OH attached, we don't call it as alcohol no more. Okay, if it attaches on to the benzene ring, we call it as phenol, yeah. Okay, this is something new. You haven't done it yet. I'll get you the answer. We call it as amide. That's it. Alright, guys, next. So ibuprofen contains carasantal, and guys, by the way, ibuprofen is used as a painkiller. These 2 drugs, painkiller, is commonly found in Panadol, yeah. Okay, so guys, let's look at it. So similarity and difference in the physical or chemical property between the optical isomer. Let's go. Similarity. What's the similarity, peeps? The similarity is they have the same chemical and correct. Property, right? Guys, what about the differences? They have different biological and you can mention optical activity. If you are too lazy to write. Okay, so you can just mention biological activity and rotate plane of polarized light into different direction. The different direction is just optical activity. So I summarize the word for you as optical activity. Understand? Alright, guys, next. What is meant by racemic mixture? What is meant by not giving you guys the answer? You guys write it down on your own. A solution that contain. Okay, before optical isomer, before mixture, equal amount. Keyword is equal amount, yeah. Keyword is equal amount. Good. I'm not giving you guys the answer. You guys try your luck, yeah. Equal amount of what? Of your optical isomer, right? Then with something. With no net optical activity. Thank you very much. Hey, these are all the popular questions in the exam, yeah. All the definition questions, try to score it. You see, if you read the notes, right, this entire page is pretty easy. You score 4 marks here. Okay. So 4 marks is a lot in A2. These are. Alright, guys, let's go. Give me a second. Let me see, can you do this or not? Ibuprofen, LiALH4. Wait a minute, they say paracetamol. Paracetamol. No, cannot. It's okay, skip. You don't need to do this. We can move on. And part D. Okay, too fast. Okay, go back. Okay, go back. Go. Okay, skip the next page. Do part D. We're gonna practice some questions. Benzene is the biggest chapter in organic. Next chapter is your honeymoon. Pheno is very easy. Oh yeah, speaking of which, guys, because next Wednesday, right, I have a dinner ongoing. So I might swap. You guys are on holiday now? Or no, not on holiday. For you, holiday. Oh, no holiday. If I swap the class to slightly earlier, is that okay? Just for next week.
But like when, sir?
But I went 5. Is that okay? 5 to 6:30.
Oh,
Yeah, I'll post a possible time that I will swap the next week class to everyone in the group, right? Because next Wednesday I have a family dinner. Yeah. So I'll swap the class to slightly earlier, yeah. Electro sub, do I have to show the two steps? Yes, you can just combine into one. Okay, so for electro sub, you just draw the original, then the thing like that, with a plus, okay, then product, that's it. So you should have 1, 2, 3, that's it. Okay, I'll walk around and check your diagram. Guys, please try. Your benzene chapter is 100 and 1,000% coming out in your A2. This chapter alone is 100 and 1,000% coming out in A2, which is why I'm moving very slow. Any school done entropy? Entropy? Not yet. Not yet. Entropy? Not yet. Not lattice energy. Any fellow has done lattice energy? Done, right? Taylor's done everything, right? Crazy. Taylor's is insane. I don't even know how you guys. Hey, they finished A2 syllabus already. Yeah, really, not kidding. I don't know how. Don't ask me. Yeah, finish it. In I don't know how many months. In how many months? In 3 months. That your school take 1 year. Your school take 1 year. Taylor's do it in 3 months. That's why I say Taylor's is built differently. Sir, my teacher speed running A2 organic chem during the break. Yeah, you are Kason, you taking October or next year May June? Later I will ask a few questions. Guys, I will ask a few questions in the group. Please vote, yeah. Okay, so October, November kid, very concerned. That's my most concern is the October, November kid. Because A2 is really difficult. Not kidding. Shit you not. A2 is really challenging. If you find AS difficult, A2 is 3 times the difficulty. Yeah. Yay! 3 months. Alright guys, let's go. Write an equation to show AlCl3, how AlCl3 generates the electrophile. So guys, again, this equation, we have done it so many times. How to generate electrophile, you see. I keep saying the first step is to generate electrophile. You see that? AlCl3 turn into AlCl4 minus. Okay, then the Cl will be gone. Am I right? So guys, it's the same thing here that we have. What do we have? A CH3COCl. And add AlCl3. It's going to turn into what? The Cl gone, right? Jump here, right? Correct. So it's a CH3CO plus AlCl4 minus. Is that right? Correct, yeah? Sure. Alright guys, next. Draw the mechanism conversion of X to Y. So guys, how to convert X to Y? At first, I draw this ding. Okay, show full mechanism. Guys, electrophile, where you place? Electrophile is here, CO. Correct. So guys, arrow draw here will hit this carbon, yeah? Understand? Correct. Okay guys, next. How? convert to ink. Okay, so the ring will be broken now, is that right? So guys, you break towards the carbon that you are substituting into, yeah. Don't randomly break here, don't just break here, okay? You have to break facing the carbon that you are substituting into. So you are substituting into this side. So it's gonna be a C double bond O, CH3, correct? Am I right? Then this one, you still have a hydrogen, am I right? What's gonna happen, guys? The electron on the hydrogen is gonna go, my positive charge is missing. It's gonna go back into the ring. Is that right? Okay, and finally, copy, paste. You have a H plus is formed. Correct. Alright guys, next. How AlCl3 is generated? I have AlCl4 minus plus a H plus turns into AlCl3 and a HCl, right? Guys, know where the equation is. See this reaction that we have? I drawn it for you guys earlier. See this? AlCl4 minus, attack a H plus, AlCl3, HCl. Am I right? Getting better. Can do right this question? Alright guys, last one.
Sir, could you go back, sir?
Yeah, of course. Okay, do the next question. Once done, I will let you guys go. Yeah. For the arrow from the delocalized, does it touch the pi bond at specific area? As in the arrow from the delocalized, oh, of course, touch the ring, touches the ring, coming from the ring, go to here. Like right next to the carbon, like right next to the C, that CH3CO will be bonded. Yes, correct. It's bonded to this, the C bonded, right? So you have to go to this C, not this C, not this C. If you draw this C is wrong, it's drawing is towards this C, because this C is the one that bonded towards the ring, okay? Okay, guys, define enantiomers. Where's enantiomers? Let's go. Molecule that has. Good job. Thank you very much. Well done. Same chemical and a physical property. That will score you 1 mark. But rotate your plane of polarized light into different direction. Done. Guys, what is the downside of producing 2 enantiomers? Require separation. Well done. Guys, adapting a synthesis, what we can do to produce just 1 single isomer? Use a chiral active catalyst. Easier. Kinda, right? Okay, so guys, basically that summarizes chapter 27. Please like and subscribe. Please like and subscribe.